Welcome to Science Hub. Today, we're diving into an extraordinary cosmic event that has captured the attention of astronomers worldwide, a collision between two massive black holes located approximately 7 billion light-years away from Earth. This event is not just remarkable for the sheer size of these black holes, but also for their rapid rotation, challenging existing theories about black hole formation. At the forefront of this research is a team from the Center for Computational Astrophysics at the Flatiron Institute. Led by astronomer Or Gottlieb, the team has been investigating the origins of these gigantic black holes and the reasons behind their collision. Their study, published in the Astrophysical Journal Letters, highlights a critical factor that had been previously overlooked: magnetic fields. The cosmic collision, now named GW 231123, was detected by the LIGO Virgo Kager observatories, which specialize in capturing gravitational waves produced by colossal cosmic movements. The main puzzle for scientists was understanding how such large and rapidly spinning black holes could form. Typically, stars that exhaust their fuel collapse and explode as supernovae, leaving behind smaller black holes. However, stars of a certain mass undergo such violent supernova explosions that they are expected to leave no remnants. To explore this anomaly, the research team conducted a two-phase simulation. The first phase modeled a massive star about 250 times the mass of our Sun. When this star exploded as a supernova, it shrank to roughly 150 solar masses, slightly above the theoretical mass gap. In the second phase, they incorporated magnetic fields into their model. The simulations revealed that not all surrounding matter falls into the black hole; some are expelled due to magnetic pressure, thus reducing the black hole's mass intake. These findings suggest a relationship between a black hole's mass and its spin. Stronger magnetic fields tend to slow down the black hole's rotation and decrease its mass, resulting in smaller, slower spinning black holes. Conversely, weaker magnetic fields allow the formation of larger, faster spinning black holes. This model may uncover a broader law linking mass and rotation, potentially confirmed by future observations. Although no other systems are currently known to test this connection, scientists are hopeful that more examples like GW 231123 will emerge. This study offers fresh insights into the formation of colossal black holes, emphasizing the crucial role of magnetic fields. If future observations validate these results, they could not only explain an event once deemed impossible but also reshape our understanding of one of the universe's most extreme and fascinating phenomena. Subscribe to Science Hub for more captivating science stories.